Okay. Maybe the lower part of the sheet. This is full. Okay. This work is started in collaboration with Marcos Marinho and Hongfei Xu. I will talk about mainly the last two papers. This is based on my former graduate students, Takayasu Kondo and Kohei Kuroda and Hongfei Xu. So the topic of this talk is WKB analysis for higher order ODE and its relation to the integral models. So I mainly use the Y functions and its relation to the WKB periods. So let's start introductions. So my talk is to explore some integrity-based approach to the exact WKB analysis. This is funded by Andre Boros, and the main tool I use is the ODE correspondence. So this is this correspondence found in noticed in the 1998 by Patrick Doré and Robert Tateo, and also soon later Vajanov and Luciano from Zamorozhko. So the essence of this correspondence is summarized in the table. So let us consider the Schrödinger equations with some centrifugal potential term, and Vx is polynomial in X. So we can analyze the spectral problem for this second order differential equations. So they found its spectral problem is have some nice relationship between the integral models. So this is some dictionary between two sides. So so this Schrödinger equation has some regular singularity at the origin, and at infinity it has an irregular singularity. So the solutions around the infinity has becomes a asymptotic series. So we need to do some Borel summation approach to this to the solution to this equation. So so connection coefficient. So they have two set of solutions around the origin at the infinity, and the connection coefficient between the two solutions, origin and infinity. So in the integral model side, this is regarded as a so-called Baxter's Q functions. And the Stokes coefficients between the some asymptotic regions. So they are evaluated by the Wronskians of the at the infinite solutions. So this Stokes coefficient is appears in the integral model side as a T function. So this is the eigenfunction of the transfer matrix of the integral model. So T functions are satisfying shown to satisfy certain functional relations called T systems. So this is regarded as some Privka relations for the determinant of the solution of the Wronskians. And so the T functions, from the T functions, we can a method of construction of the Y functions, which is a kind of some taking a cross ratio of the two four T functions. And so this is the main object I want to talk about here. So in the ODE side, this is regarded as a Boros coefficient. This is the exponentials of the Borel-summed period integral, WKB period integral. So so resurgent appears in this relation between two objects. And it is shown that the y functions satisfy the functional relations called y system. And Alyosha Zamolodchikov showed that from this y system leads to the thermodynamic Bethe equation in the integral models. So in the ODE side, this is regarded as the Diringer form discontinuity formula of the exact WKB period. So this is somehow established for the some particular Schrödinger case. So my talk is related to the applying this to explore this relation for the some sort of higher order version. That's my talk. So let me to do why we are going to the higher order dimensions. So originally, ODE correspondence formulated for the Schrödinger case and also for the case of the monomial potential. So it is so this case is very so integral models machinery works in some sense. So so my previous work with Marcos Marinho and Juanfes Xu is to generalize this monomial potential to the case of generic polynomial potentials. And later, I and myself and Xu at this polynomial potential and is the case of some centrifugal potential. So and for the Schrödinger case, this Boros symbol is regarded the relation between the Boros symbol and some variables appearing cluster algebra was known in some mathematicians. So Iwaki and Nakanishi. So the cluster algebra is a very close algebraic system related to the Y system. I will not talk about it in detail. So there's some suggesting to a relation between Boros and Y system. So and also this kind of ODE also appears in the context of the four-dimensional n equal 2 supersymmetric case series in the half omega background. Sometimes it is called the Nekrasov-Shatashvili limit of the omega background. So simply I called it half omega background. So and this is in this background. So the low energy effective theory describing this Suji gauge theories always described by some certain algebraic curve. So, but in this background, so this curve is lifted to the quantum version. That means the curve becomes some differential equations. So this was first suggested by Mironov and Morozov, and its relation to the exact WKB periods, and also it satisfied the TBA equation was deeply explored by Gayot, Mu, and Naitsuke. And in relation to this quantum formalism is proposed, studied by the Gayot. So in this for the dimensional settings, so the ball crossing phenomena is important to see the precise correspondence between the WKB periods and this four-dimensional gauge theories. So this also happens in the case of our ODE correspondence. So actually, so using this wall crossing phenomena, we can study some sort of different type of integral models from the same type of ODE with some different potential and different parameters. So my question is to, but this somehow explored in the case of second order differential equation. So I want to extend this relation to the higher order ODE. So yes. Yes, that I will discuss in the at the level of TBA equations. So it has a very different form of the TBA, characterized very different TBA systems. And so the way I will discuss. Yeah, I want to discuss it later. Yeah. So and also mentioned about exact WKB analysis for higher order ODE has been started by the Bachner, Vince, Robert, and also deeply studied by some Aoki, Kawai, and Takei-san. So in this analysis, the ODE, higher order ODE, there exists some turning point. So they studied mostly the case of the turning point are simple. So minimum number of Stokes line started from the one turning point. And so in the context of the ODM correspondence, so there appears many examples of higher ODE, which was explored by this Drey's group. And also, this can be written in the form of the first order linear differential systems associated with arbitrary affine algebra. So in these cases, this turning point not non-simple. Non-simple means that we have many Stokes line starting from the one turning point. So and for this higher order cases, corresponding integral models are known for this kind of models. So at least for the monomial potentials. So so we want to extend this to this monomial potential to the some generic potential. So in that case, there's some problem what corresponding integral models for higher ODE with some sort of general polynomial potential cases. That's another motivation for this work. So let me start from the WKB analysis for higher order ODE. So that for the ODE IM correspondence, the higher ODE appears from the some sort of affine to the field theories. So it can be admitted, the affine to the field equation admitted the Lux form, where phi represents some scalar fields R component. R means the rank of the affine algebra. And M in mass and lambda is some spectral parameter. And E and E alpha naught is some generator for the simple roots. And NI check is some, I didn't write some definition, but it's called co-labels to the expansion coefficient of the highest root, co-highest root in terms of a simple roots. Anyway, so affine to the field equation can be written in the form of the flatness conditions of the two gauge fields in 2 dimensions. And modified means that we make a conformal transformation of this affine to the field equation. So the effect of conformal transformation appears here. So this is some classically integral field systems, and the ODE correspondent to this system is can be obtained by the conformal limit of the linear problem. So just take the simple finite dimensional first order linear systems, which is characterized by the some polynomial p and some some vector g. This characterizing the monodromy around the origin. And yeah, that's I want to consider these systems. So if one takes the representation of the affine Lie algebra, this first order linear system can be written in the equivalent to the higher order differential equation for certain component of this vector solution to the first order linear system. So this is a list, and so we have sort of many types, but I have no room to write down for other exceptional Lie algebra. So, but so A type, D type, and the twisted Lie algebra type. So some D type contains some pseudo differential operator inside the. So it looks like it looks a bit difficult to work out this WKB analysis for this problem. So first we start from the AR type, and also some trivial monodromy around the origin. So this leads to this higher order differential equations. Or just say that replacing the second order differentials by the higher order ones. So let me start from the WKB analysis from this equation. So I will mainly talk about the third order differential equations. So we can do the WKB expansion as we did in the second order cases. So let us expand these, express these exponential solutions in this form with so exponential factor is expanded by the epsilon. So epsilon is the rho of Fraser rho of Planck constant, and also some omega background parameter. And substituting this expression into the this third order equations, we have Riccati equations like this. Then actually this can be solved recursively from the P naught. I will not write down so P naught. It is so maybe right there. This is a cube root of the px, the function of appearing in the Fraser rho potential part. So then, so we can solve as you wish on the computer. So then we observe that the so P odd term becomes total derivative. So this happens as very similar to the second order cases. And but we found the some even order, some part of the even series becomes also total derivative. So this happens for the special for the this kind of higher order differentiation. Actually, the P4 I wrote down before can be written in the total derivative form like this. And so this turns out to be consistent with TBA equations and also the order of integral motions corresponding to this ODE. So this is funny, but this happens for higher order cases. And more interestingly, so if I take the sorry, P naught is not. I should remove P0. So P is some cube plus some linear part. So all the Pn becomes total derivative. So this is somehow similar cases of the harmonic oscillator. So something interesting things happen. And so if we consider higher order type ODE, the similar disappearance of total derivativeness happens for some particular order, characterized by the Coxeter number of the reagent. So then we define the WKB period for this based on this higher order corrections. Then WKB curve is so second order case. This is a y squared, but we have the y cubed to some polynomial case. So this is sometimes called super elliptic curve in the mathematical literature. But that we are do the same way as we did in the second order cases. And we define the classical WKB period. And technically, we also, it's better to consider some y squared as also some fundamental, regarded as fundamental period. So alpha, so is some cycles on this WKB curve. So in this case, we have a three-seated curve with some cut. So these cycles connect to seat through the two cuts. And the reason to introduce some two types of differentials. So because this is becomes this generate as a generating function of the basis of meromorphic differential on the WKB curve. So hyperelliptic curve, we have a y over some polynomial serve the basis of the meromorphic differentials. But in this case, we have in addition, y squared over some polynomial becomes the basis of this on the polynomial. Then we define some sort of fundamental cycles which connect the A and A plus one seat by like this way. So this can be so the period can be evaluated in the form of the hypergeometric integral, some generalized version of the hypergeometric integrals. Then so this is the basis of the meromorphic differential on the WKB curve, and the higher order correction to the P defines P and dx define meromorphic one form on the WKB curve, and then it can be expanded in terms of this basis up to total derivative. So this total derivative doesn't affect the period integral. So we need to obtain this coefficient. So for the some cubic polynomial cases, this can be obtained like this. So so this can be characterized essentially by the prefactor. So delta means some discriminant of the curve, and D naught is some polynomial in the some coefficients. So this D naught appears in the always appears in the for higher dimensional factor. So previously I said some correction vanishing cases. So in that cases, D naught vanishes always. So that means the some specific potential cases, this coefficient always vanishes. So that this is a phenomenon I observed for this special cases. So I have no technique to study for this Borel summability and asymptotic analysis for this expansion, but we can calculate the coefficient in brute force and applying the singularity in the Borel plane. So this special cases works. We found some points on the singularity in the Borel plane. So that's structure on the singularity is very fit to the singularity structure work in the appearing in the WKB TBA equation. So so in this case, I expect some Borel resummation technique works, but I have no rigorously mathematical foundation for this observations. So then now we will check this WKB period and compare with the y function appearing in the integral systems. So maybe this is a very short summary. So in the case of, let me remind that case of the WKB curve in the case of Schrödinger equations, where the Riemann surface is the hyperelliptic type, and the potential of the Schrödinger equation and energy determine this WKB curve. So, and we can determine two types of period for this WKB curve corresponding to the allowed region and the forbidden region in the potential. So, and the Delabayre-Fan formula states that this Borel sum period, how they show the discontinuity and how they period are related to each other by this discontinuity formula. So this discontinuity formula translated into the form of the TBA equations, where the lateral Borel resum period satisfying the form of the integral equation. So this is this integral equation is called TBA equations that appears in the integral model. So we have another route to derive these TBA equations from the applying the ODE correspondence. So so this Schrödinger equations has the some asymptotic solutions, but so subdominant solution, which is decaying solutions along this infinity region in certain Stokes sector, has uniquely determined. So, and then two different neighboring Stokes subdominant solutions are related by each other by the rotation of the this so zeta means some spectral Planck complexified version of the Planck constant, and one can construct the this serves the basis of the asymptotic solution of the Schrödinger equation, and taking Wronskian for these solutions, this is independent of the positions, and defining some cross ratio of the Wronskians, it is shown that this y function satisfying the functional relations. So this is called y system, which is a basic tool to study integral models. then so we can rewrite this Y system once we know the analyticity in the spectral parameters and also the asymptotic behavior at the infinity. So this Y system can be translated into the integral equation, which was done by Zamolodchikov many years ago. And this is exactly the same form as the obtained by the Delabayre-Fan formula. So this TBA equation characterizing the properties of the integral models. So one, this has some solution in the theta is going to minus infinity limit. So the Y function, which is an exponential of the epsilon, this is called the pseudo energy, which is the characterize the energy of the pseudo particle describing the integral model. Then from the information of the this constant value, one can evaluate the effective central charge of the system. So this is the central charge of the CFT called generalized Parafimon systems. And actually, so TBA system is agree with the so-called homogeneous Sine-Gordon models of this level 2, which was maybe it was constructed by the Castro Alvarado, Flynn, and Korf, and Miramontes some years ago. Minimal chamber means that the setup I assume the turning point of the problem is real, all real and all real line. That's a temporal definition of the minimal chamber. We can deform slightly around this situation into the complex one. So this is a case of the minimal chamber story. Yes.
When you talk about this charge, central charge, this is from the Toda field theory, is a property, right? Or
this is derived from the TBA equation itself.
It's a property of the TBA equation.
Yeah. So
how should I think about it?
Yes. So in this case, is the two limits. So theta is infinity and theta is minus infinity. So theta is minus infinity. This driving term vanishes, and some constant solution becomes some consistent solution for this system. So we assume the constant solutions under this integrants in front of the integral. So then it becomes the algebraic equation for this system. So and the constantness of the solution is explored by this by solving this integral equation numerically.
Yeah.
So then we assume that becomes constant. Then we solve this equation algebraically.
Yeah.
That will lead to this solution.
Yeah.
Yeah.
Thank you. Then so we are considering some minimal chamber situations where the potential has real and distinct turning point. So, but in general, polynomial potential, so turning point can be complex and arranged into the distributed in the complex plane.
So this is an example of the cubic potential. And the monomial potential cases, this is the some cube root of unity. So in this case, is the period integral become complex, and the period can be characterized its modulus and its angle. So, but in this, if this angle is very small, we can apply the same type of TBA equations. But it's nice to shift the argument by the this angle slightly. Then we have this kind of TBA systems. But the kernel functions, due to the shift of the argument, kernel function is also have a complex term. And star represents some convolution to the kernel. So actually this kernel function have a singularity in the complex plane. So this integral can applied only for the valid for the angle phase or phase is rather small and satisfying this restrictions. So then, if this this phase difference becomes large, so this integration contour of the convolution integral hit the pole of the kernel. So then we need to modify TBA equation into the form. This is a contribution from the kernel. So this is in the sense of this four-dimensional theory. This is called the wall crossing phenomenon. And so in the TBA context, this can be detected like this some contribution from the pole in the integration. So for the cubic potential, it turns out we need to introduce a three-term y functions, three y functions corresponding to the original WKB cycle, and in addition to the composite WKB cycle. So, so this can be constructed, and they satisfy this three-term TBA equation. So this happens under special cases. We have monomial potentials. So in this case, monomial potential has some Z3 symmetry. So this three-term TBA equation in terms of single equations. So this was originally founded by the Zamolodchikov to describe the Yan-Lee edge singularity, non-unitary minimal models. So we can obtain this kind of special TBA from the case. Yes.
Just a very naive question. When you say that you get a contribution from the pole,
yes,
because these L's get shifted, but that contribution will be exponentially small.
Well, just this is some residual formula for the real integrals. So if the phase shift, this originally the pole exists here, and the phase change, if phase changes, so this pole crosses the integration line. So original integration line is deformed into this way.
Yes.
So, but this definition of the kernel is really defined on the real line. So this effect means splitting this real line integrals plus some pole contribution.
But that pole, what I'm asking, that pole contribution will be in exponentially small in the epsilon. Am I correct?
Well, this is the yes. This is L in terms of L. So yeah. So L is the L is maybe log plus exponential. So yeah, in a sense, yeah, it is yes.
Okay.
So the is corresponding exponential in the energy. Yeah, that's right.
Thank you.
So in the case of so WL potential, so this happens in this way. So this is WL potentials. So for this energy level shows that all turning points are real, and if the energy grows up, so turning points are 2, and the other 2 turning points goes into the complex plane. So this is regarded as a wall crossing phenomenon. And so we have some different TBA descriptions. And again, some monomial potentials. So we have some specific term of TBA equations, which describing Z4 paraphernalia. So in general cases, monomial potential has some specific non-unitary minimal models, and also the Zn plus 1 parafermion cases. So this is the difference of the minimal chamber and the maximal symmetric point. So maybe I have lack of time. So I briefly, the situation is actually just very similar to the second differential cases, even in the higher order cases. So it's formally we construct the asymmetric solutions, subdominant solution in the Stokes regions, and making rotations, which creates the basis of the different Stokes regions. And we have a higher rank differential systems, so the basis of the solution have a higher dimensions. And Wronskians, we can define Wronskian to represent some T functions, but some maybe detailed formula will not be necessary. So, but the T function will satisfy some algebraic relations called T systems, which come of the higher dimensional version of the determinants. Actually, this is come from the definitions, and also cross ratio of the T functions we can define Y functions that obey the another function relation called the Y system. So and this is a slide to explain some asymptotics of the Y functions, but the conclusion is that so for some leading contribution can be expressed by the classical period. So this diagram, this is some diagram to construct the asymptotic expression for this, for example, one Y function. This was developed by Naitsuke and Horan Naitsuke, called some Arbernianization tree technique. So then we find the TBA equation from the Y systems. And the difference from previously was the kernel of the TBA system can be different form and some different singularity structure. And again, this is TBA valid is in the minimal chamber, neighboring phase small, but this case is relaxed to the pi over 3. And this obtained by this TBA equation, this quantity structure shown in the previously is agree with that experimental result of the Borel dimensions. And this TBA analysis shows that the model corresponding to the effective central charge, and this is also related to some generalized parafermion. But for this case, we have a third order differential equation. We have a level 3. And this is a numerical test of the y functions and the quantum period. The method I presented in quantum period and the result from the TBA equation. So these values perfectly match by two ways. So another explanation of the coefficient is coming from the integral model side. Actually, the t function can be expanded as the integral motion of the W3 minimum models. And so this gives some interpretation of the expansion of the WKB period in terms of the integral model side, but as some function of the primary fields and the central charge of the some W minimum models. But actually, these identifications, these two T functions and the WK period agrees with each other. So then I will work out wall crossing phenomena for this TBA equation. So, but it's very difficult in general sense how the determine the wall and the general structure of the wall. So I use some sort of direct approach of the wall crossing. So I assume the family of potential parameters P, T. So the initial point is in the minimal chamber. The final point is characterized by the maximal chamber, the maximal symmetric point. So 0 points I moved from the turning point from this one to this one by linearly interpretation. So we observe at some points the phase of the two periods has hit the singularity of the kernel. So this 2 points have a wall happens for wall crossing. So then the formula for the wall crossing has we can use a similar way, and this is just writing the result. After the first wall crossing, we have in addition this formalism transformations, we can add some additional y function. So the y system is extended. So we have two wall crossing. So then eventually we have originally we have two starting from two TBA equation. Then we have arrived at four types of TBA equation. But the monomial potential cases, some symmetry appearing happens among the y functions. So we have some reduced TBA system. So actually this two set of integral equation is the form of the D4 type divided by the G3 symmetry. So in this case, different type of TBA equation appears at the maximal point. So this is the we are also explored the this is a cubic cases, and we have also the consider higher order, fourth order cases. And so starting from the minimal chamber, we have started from 3-term TBA. And at the maximal chamber, we have a 12-term TBA equation. And then at the maximal point, monomial type, we have obtained the E6 type TBA equations, which describing the tri-critical three-state pot model with this central charge. But A2 case, we have D4 type, and this have effective central charge 1. This is described as Sine-Gold model at reflectionless point. This is just some CFT compactized on Todas. And so this is in the context of 4-dimensional gauge theories, these relations suggesting the dualities. This first one is the order of the differential. And second one is the order of potentials. And this can be interchanged in some sense. And for A2 cases, there appears non-trivial duality between A2, A2, and D4, A1. The other is A2, A3, and E6, A1. So this wall crossing phenomena actually seems to correspond to this duality of AD, even the Arrhenius-Douglas series. So let me finish my talk this slide. So I will not talk about any things about 4-dimensional quantum period, but the same other ODE are the same order. So so we start from the affine type equation of higher rank, and applying the ODE correspondence. We have find the y functions, and which described in a 2-dimensional integral models. And applying some exact WKB period, well, we have some obtained the quantum period, which shows the asymptotic series. So these are some have a relation. So in the sense of this, this shows some relation between 4D theories and 2D integral models. Sometimes appears in the context of regarded as a 2D, 4D correspondence appear in the Necklace-Chatterjee limit. And we expect for higher rank, we have higher order, higher rank coset generalized parafermions. And at the maximal point, this at present, we have obtained the models proposed by many years ago by Zamolodchikov, the same as the ADY systems. So then we expect for higher order potential cases, third order, related to the A4 systems, we expect E8 TBA. So this is corresponding to the central charge half Ising models. So which is expected from the 2D, 4D duality. And I'm not find any models, ODE models for DR and E7, but it looks like interesting to explore this. And maybe interesting to work out other higher order ODE related affine to the equations. And recently, I worked with some supersymmetric generalization of affine to the field series. And so this is some special cases. This ODIM corresponding is related to the supersymmetric potential, quantum mechanics, where the potential term is squared form. Okay, so that's all I want to talk. Thank you very much.
All right, I see one question already. Can I ask you about how the potential, the P function, changes
with the different group types. So you mentioned the A type at the beginning, which had P being some
Yes.
monomial. And then you mentioned a D type later on. But what happens when you go to multiply lace groups, like you also listed near the beginning, C type and G2
Yeah.
even. How did the potentials change?
Potential is, I assumed always the polynomial type. Polynomial type is means that it's a A type potential. And D type, we have some inverse potential in addition to that.
You
That
mean
kind
like-
appears in the singularity series.
Right.
Yeah.
So a reciprocal term.
Yeah.
1 over X, for
Yeah,
example.
that's right. I mean that the A type and the other type is the corresponding to the affine to the root system of the starting point of the linear differential system.
Yeah, I guess partly why I'm asking is I'm unfamiliar with the multiply lace groups appearing in that context.
Multiply lace, you mean
G2.
twisted ones?
Yeah.
Okay.
Yeah.
Yeah.
So I wondered if you knew about how the
Yeah,
potential
that's
changes for those.
yeah, some identification of the generator by automorphism. So according to the symmetry of the Dinkin diagram. So A type, we have a line, and we can fold this Dinkin diagram. So that will give us some twisted type rearrangement, folded type affine rearrangement.
Thank you.
Are the TBA equations here exactly the same as Gayoto-Mornitsky's, or is there some subtlety involved?
Well, it's the writing way of the TBA equation is quite different. But yeah, as far as look at some particular examples, like a lower rank, so looks like coincide with that.
Thanks.
So the ODEs that you get at high order, they always just have one derivative term and a potential. Is that always the case coming from the type A affine Toda, or can you get other derivatives appearing in the operator?
We should back to this slide. You mentioned this once.
Oh, okay. So you have for different root systems. You get other derivatives.
Yes. So mostly the differential has some singularity at the origin. So mostly has a similar to the A type. But somehow this D type has an inverse.
But in all the examples you considered, you always took H to be 0.
Yeah, that's right. Yeah, that's the simplest cases. Yeah,
Do you know what happens amongst the H?
Well, it's actually this is interesting case even in the A1. That's a centrifugal potential problem in the WKB analysis, like a Stark problem. Yeah, that's happens for H non-zero. So that's interesting. But my present technology doesn't work so much. Yeah.
All right, so there's an online question.
Yes. Okay. I was very interested. Thank you very much. I would like to understand if you use the TBA formalism, does that allow you, for instance, to compute the eigenvalues of the ordinary differential equation in some convenient way numerically?
Yes. So we also we need additional condition for the satisfying the WKB period, like Bohr-Sommerfeld conditions. So it's related to the connection. Maybe I should not say to the Andrew Boss, like this way. But it's if you consider some some connection problem from a point in a complex plane into another complex plane. That's connection. If one cross the Stokes line, we have some connection matrix acting on the wave functions. So then we will obtain the exact quantization condition to find the spectral problem. But for higher order ODE, it's I'm not quite sure about how to construct them, and but I'm not also sure how the spectral problem for higher order ODE is where it happened in some physical context. That's maybe.
Thank
I'm
you.
not, yeah.
Thank you very much.
Yeah.
Are there any further questions? All right, let's thank our speaker again.